Switching the neutral in a transfer switch to create a separately derived system offers advantages in both safety and performance. It involves bonding and grounding the neutral at the generator. While it generally costs more than systems that don't switch the neutral, certain situations warrant the extra expense. From a safety standpoint, switching the neutral can eliminate ground faults. If the neutral is bonded at both the generator and the load side, a ground fault on the load side can create a neutral to ground fault at the generator. This can energize the generator frame, creating a shock hazard. By switching the neutral, this potential fault path is eliminated. Another safety benefit is preventing common mode currents. These currents, caused by unbalanced loads, can circulate through the neutral and grounding system. When the neutral is switched, these currents are isolated to the generator's side, reducing electrical noise and interference that could affect sensitive equipment. Performance improvements are another reason to switch the neutral. It can lead to improved voltage regulation, especially for nonlinear loads. Switching the neutral enables the generator to regulate its voltage more effectively, providing a more stable voltage supply to critical equipment. Furthermore, it helps reduce harmonic distortion. Harmonic currents, generated by various loads, can distort the voltage waveform. Switching the neutral confines these harmonics to the generator's side, minimizing their impact on the load. However, there are also other considerations. Transfer switches that switch the neutral are typically more expensive. Also, some electrical codes may mandate switching the neutral for specific applications, such as critical healthcare facilities. Interconnected systems, such as multiple generators operating in parallel or connected to a utility grid, may require neutral switching to prevent backfeeding and other safety concerns. Generally, it's advisable to switch the neutral for safety and performance in certain scenarios. Firstly, when dealing with critical loads, such as sensitive equipment or life support systems, switching the neutral is a wise precaution. Secondly, when heavy harmonic producing loads are present, switching the neutral can mitigate harmonic distortion issues. Thirdly, when operating multiple generators in parallel or connecting to a utility grid, switching the neutral is often necessary. Fourthly, high voltage applications, when the system voltage exceeds 600 volts, benefit from switching the neutral. However, if cost is a major factor and the potential safety and performance benefits are not substantial, it may be acceptable to forego switching the neutral. It is important to analyze the specific application and weigh the costs and benefits before making a decision. In summary, deciding whether to switch the neutral in a transfer switch involves a trade-off between cost and potential improvements in safety and performance. Carefully consider the specific application, the types of loads, and any applicable code requirements to make an informed decision. Separately derived systems offer benefits such as improved grounding, reduced neutral currents, and enhanced isolation, but they also come with additional costs and complexity. The decision of whether to implement a separately derived system should be based on a thorough engineering analysis. This analysis should consider factors such as the size and type of load being served, the characteristics of the power source, and any applicable code requirements. Grounding is a critical aspect of electrical safety. A properly grounded system provides a low impedance path for fault currents to flow back to the source, allowing overcurrent protective devices to quickly trip and energize the faulted circuit. In a separately derived system, the grounding electrode conductor is connected to the neutral point of the generator or transformer, and the grounding electrode system is installed at the location of the separately derived system. This grounding electrode system typically consists of one or more ground rods, ground plates, or other approved grounding electrodes. The size of the grounding electrode conductor is determined by the size of the transformer or generator, as specified in the National Electrical Code, or NEC. Neutral currents can cause a variety of problems in electrical systems, including voltage drops, equipment overheating, and interference with sensitive electronic equipment. In a separately derived system, the neutral conductor is isolated from the building's grounding system, which can help to reduce neutral currents. This is because the neutral current is only able to flow through the neutral conductor of the separately derived system, and it is not able to flow through the building's grounding system. Isolation is another important benefit of separately derived systems. By isolating the separately derived system from the building's electrical system, it is possible to protect sensitive equipment from voltage surges, noise, and other disturbances. This isolation can be achieved by using an isolation transformer or by providing a separate grounding system for the separately derived system. Nonlinear loads are loads that draw current in a non-sinusoidal manner. These types of loads can generate harmonic currents, which can cause a variety of problems in electrical systems. In a separately derived system, the harmonic currents generated by nonlinear loads are confined to the separately derived system, which can help to prevent them from propagating throughout the building's electrical system. Surge protection is an important consideration for all electrical systems, but it is especially important for separately derived systems. This is because separately derived systems are often used to power critical equipment, which can be damaged by voltage surges. Surge protection devices should be installed at the point where the separately derived system connects to the building's electrical system, as well as at the equipment being powered by the separately derived system. The NEC contains a number of requirements for separately derived systems. These requirements cover topics such as grounding, bonding, overcurrent protection, and wiring methods. It is important to consult the NEC before installing a separately derived system to ensure that the system is installed in accordance with all applicable requirements. When evaluating whether to install a separately derived system, it is important to consider the potential benefits and drawbacks of the system. The benefits of separately derived systems include improved grounding, reduced neutral currents, enhanced isolation, and mitigation of harmonic currents. The drawbacks of separately derived systems include increased cost and complexity. The decision of whether to install a separately derived system should be based on a thorough engineering analysis. This analysis should consider factors such as the size and type of load being served, the characteristics of the power source, and any applicable code requirements. The NEC, particularly Article 250, provides detailed guidelines on grounding and bonding requirements for electrical systems, including separately derived systems. Understanding and adhering to these requirements is essential for ensuring the safety and proper functioning of the electrical system. Article 250.20 outlines the general requirements for grounding electrical systems. It specifies which systems are required to be grounded, such as those serving premises wiring systems and those operating at certain voltage levels. Article 250.21 discusses systems that are not required to be grounded. These systems may include certain isolated systems or systems used for specific purposes where grounding is not necessary or practical. Article 250.24 provides specific requirements for grounding separately derived systems. It covers topics such as the location of the grounding electrode, the size of the grounding electrode conductor, and the bonding of the neutral conductor. Article 250.26 addresses the grounding requirements for high-impedance grounded neutral systems. These systems are often used in industrial applications where it is desirable to limit the ground fault current. Article 250.28 provides guidelines on bonding requirements for electrical systems. Bonding is the process of connecting metallic parts of the electrical system together to create a low-impedance path for fault currents. Article 250.30 outlines the requirements for grounding electrode systems. The grounding electrode system typically consists of one or more ground rods, ground plates, or other approved grounding electrodes. Article 250.32 addresses the grounding requirements for buildings or structures supplied by feeders or branch circuits. It specifies the requirements for grounding the metal enclosure of the building or structure. Article 250.34 provides guidelines on grounding portable and vehicle-mounted generators. It covers topics such as the bonding of the generator frame and the connection of the grounding electrode conductor. Article 250.36 addresses the grounding requirements for systems over 1000 volts. These systems require special grounding techniques to ensure safety. Article 250.50 provides guidelines on the use of grounding electrodes. It specifies the types of grounding electrodes that are permitted and the methods for installing them. Article 250.52 outlines the requirements for the grounding electrode conductor. The grounding electrode conductor is the conductor that connects the grounding electrode to the electrical system. Article 250.53 addresses the bonding of metal enclosures and other non-current carrying metal parts of the electrical system. Bonding is essential for creating a low impedance path for fault currents. Article 250.54 provides guidelines on the use of supplemental grounding electrodes. Supplemental grounding electrodes can be used to improve the grounding of an electrical system. Article 250.56 addresses the grounding of electrical equipment. It specifies the requirements for grounding equipment such as motors, transformers, and paddleboards. Article 250.58 provides guidelines on the grounding of intrinsically safe systems. Intrinsically safe systems are designed to prevent ignition in hazardous locations. Article 250.60 addresses the grounding of lightning protection systems. Lightning protection systems are designed to protect buildings and structures from lightning strikes. Article 250.62 provides guidelines on the use of surge protective devices. Surge protective devices are used to protect electrical equipment from voltage surges. Article 250.64 addresses the installation of grounding electrode conductors and bonding jumpers. It specifies the methods for installing these conductors and jumpers to ensure proper grounding and bonding. Article 250.66 provides guidelines on the sizing of grounding electrode conductors and bonding jumpers. It specifies the minimum size of these conductors and jumpers based on the size of the electrical system. Article 250.68 addresses the connection of grounding electrode conductors and bonding jumpers to grounding electrodes. It specifies the methods for connecting these conductors and jumpers to ensure a reliable connection. Article 250.70 provides guidelines on the methods for grounding and bonding equipment. It specifies the methods for grounding and bonding equipment to ensure safety and proper functioning. In addition to the requirements in Article 250, other articles in the NEC may also contain requirements for grounding and bonding specific types of equipment or systems. It is important to consult all applicable articles of the NEC before installing or modifying an electrical system. Harmonic currents are currents with frequencies that are integer multiples of the fundamental frequency of the electrical system, typically 60 Hz. These currents are generated by nonlinear loads, which are loads that draw current in a non-sinusoidal manner. Examples of nonlinear loads include electronic devices such as computers, televisions, and LED lighting, as well as industrial equipment such as variable frequency drives and arc welders. Harmonic currents can cause a variety of problems in electrical systems, including voltage distortion, equipment overheating, and interference with sensitive electronic equipment. Voltage distortion occurs when harmonic currents flow through the impedance of the electrical system, causing the voltage waveform to become distorted. This voltage distortion can affect the performance of sensitive electronic equipment and can even damage some types of equipment. Equipment overheating can occur when harmonic currents flow through conductors and transformers, causing them to overheat. This overheating can reduce the lifespan of the equipment and can even cause fires. Interference with sensitive electronic equipment can occur when harmonic currents radiate electromagnetic interference, which can disrupt the operation of sensitive electronic equipment. There are a number of ways to mitigate the effects of harmonic currents. One way is to use harmonic filters, which are devices that are designed to block harmonic currents from flowing through the electrical system. Another way is to use harmonic mitigating transformers, which are transformers that are designed to reduce the amount of harmonic current that they generate. A third way is to use power factor correction capacitors, which can help to reduce the amount of harmonic current that flows through the electrical system. Separately derived systems can also help to mitigate the effects of harmonic currents. By isolating the separately derived system from the building's electrical system, the harmonic currents generated by nonlinear loads are confined to the separately derived system, which can help to prevent them from propagating throughout the building's electrical system. The NEC contains a number of requirements for harmonic currents. These requirements cover topics such as the maximum allowable harmonic current distortion, the sizing of conductors and transformers to account for harmonic currents, and the use of harmonic filters. It is important to consult the NEC before installing or modifying an electrical system to ensure that the system complies with all applicable requirements for harmonic currents. When dealing with critical loads, consider the impact of a power outage on those loads. Critical loads are loads that must be kept running during a power outage in order to prevent serious consequences, such as loss of life, injury, or damage to property. Examples of critical loads include life support systems in hospitals, emergency lighting systems in buildings, and fire alarm systems. There are a number of ways to provide backup power for critical loads. One way is to use a generator, which is a device that generates electricity from a fuel source such as gasoline, diesel, or natural gas. Another way is to use an uninterruptible power supply, or UPS, which is a device that provides battery backup power to a load in the event of a power outage. A third way is to use a transfer switch, which is a device that automatically switches a load from the normal power source to a backup power source in the event of a power outage. When selecting a backup power system for critical loads, it is important to consider the following factors. Firstly, the size of the load. The backup power system must be able to provide enough power to meet the needs of the critical loads. Secondly, the duration of the power outage. The backup power system must be able to provide power for the expected duration of the power outage. Thirdly, the reliability of the backup power system. The backup power system must be reliable enough to provide power when it is needed. Fourthly, the cost of the backup power system. The backup power system must be affordable. When installing a backup power system for critical loads, it is important to follow all applicable codes and standards. The NEC contains a number of requirements for backup power systems. These requirements cover topics such as the installation of generators, the installation of UPS, and the installation of transfer switches. It is important to consult the NEC before installing or modifying a backup power system to ensure that the system complies with all applicable requirements. Regular maintenance is essential for ensuring the reliability of a backup power system. Generators should be regularly inspected and tested to ensure that they are in good working order. UPS should be regularly inspected and tested to ensure that the batteries are fully charged and that the system is functioning properly. Transfer switches should be regularly inspected and tested to ensure that they are switching properly. In addition to regular maintenance, it is also important to have a plan in place for responding to power outages. This plan should include procedures for notifying personnel, activating the backup power system, and monitoring the critical loads. It is also important to have a plan in place for dealing with extended power outages. This plan should include procedures for refueling the generator, replenishing the UPS batteries, and providing for the needs of personnel. By taking these steps, you can ensure that your critical loads will be protected during a power outage. Nonlinear loads require careful consideration when designing and operating electrical systems. Nonlinear loads are electrical loads that draw current in a non-sinusoidal waveform. This means that the current waveform is not a perfect sine wave, but instead contains harmonics, which are currents with frequencies that are integer multiples of the fundamental frequency, typically 60 Hz. Examples of nonlinear loads include electronic devices such as computers, televisions, and LED lighting, as well as industrial equipment such as variable frequency drives and arc welders. The harmonics generated by nonlinear loads can cause a variety of problems in electrical systems, including voltage distortion, equipment overheating, and interference with sensitive electronic equipment. Voltage distortion occurs when harmonic currents flow through the impedance of the electrical system, causing the voltage waveform to become distorted. This voltage distortion can affect the performance of sensitive electronic equipment and can even damage some types of equipment. Equipment overheating can occur when harmonic currents flow through conductors and transformers, causing them to overheat. This overheating can reduce the lifespan of the equipment and can even cause fires. Interference with sensitive electronic equipment can occur when harmonic currents radiate electromagnetic interference, which can disrupt the operation of sensitive electronic equipment. There are a number of ways to mitigate the effects of harmonic currents. One way is to use harmonic filters, which are devices that are designed to block harmonic currents from flowing through the electrical system. Another way is to use harmonic mitigating transformers, which are transformers that are designed to reduce the amount of harmonic current that they generate. A third way is to use power factor correction capacitors, which can help to reduce the amount of harmonic current that flows through the electrical system. Separately derived systems can also help to mitigate the effects of harmonic currents. By isolating the separately derived system from the building's electrical system, the harmonic currents generated by nonlinear loads are confined to the separately derived system, which can help to prevent them from propagating throughout the building's electrical system. The NEC contains a number of requirements for harmonic currents. These requirements cover topics such as the maximum allowable harmonic current distortion, the sizing of conductors and transformers to account for harmonic currents, and the use of harmonic filters. It is important to consult the NEC before installing or modifying an electrical system to ensure that the system complies with all applicable requirements for harmonic currents. When dealing with multiple generators, it's essential to consider several factors to ensure safe and reliable operation. Firstly, synchronization. When connecting multiple generators in parallel, it's crucial to synchronize them properly. This involves matching the voltage, frequency, and phase angle of the generators before connecting them. Synchronization ensures that the generators share the load equally and prevents damage to the generators and the electrical system. Secondly, load sharing. Proper load sharing is essential for efficient operation of multiple generators. Load sharing can be achieved using various methods such as droop control, isochronous control, and reactive power compensation. Droop control is a simple method that allows generators to share the load based on their speed. Isochronous control maintains a constant frequency, allowing generators to share the load equally. Reactive power compensation helps to improve the power factor and reduce voltage drops. Thirdly, protection. Adequate protection is crucial for preventing damage to the generators and the electrical system. Protection devices, such as circuit breakers, fuses, and relays should be installed to protect against overcurrent, overvoltage, undervoltage, and other abnormal conditions. Fourthly, grounding. Proper grounding is essential for electrical safety. The grounding system should be designed to provide a low impedance path for fault currents, allowing protective devices to quickly trip and energize the faulted circuit. Fifthly, control system. A sophisticated control system is necessary for managing multiple generators. The control system should be able to monitor the generator's performance, control their operation, and respond to abnormal conditions. The control system should also be able to communicate with other systems, such as the building management system, to ensure seamless integration. Sixthly, paralleling switchgear. Paralleling switchgear is used to connect multiple generators in parallel. The switchgear should be designed to safely and reliably connect and disconnect the generators, and it should include protection devices to protect against abnormal conditions. Seventhly, fuel supply. A reliable fuel supply is essential for continuous operation of multiple generators. The fuel supply system should be designed to provide enough fuel to meet the generator's needs, and it should include backup systems to ensure that the generators can continue to operate during a fuel shortage. Eighthly, maintenance. Regular maintenance is crucial for ensuring the reliability of multiple generators. The generators should be regularly inspected and tested to ensure that they are in good working order. The maintenance schedule should be based on the manufacturer's recommendations and the operating conditions. Ninthly, NEC requirements. The NEC contains a number of requirements for multiple generators. These requirements cover topics such as the installation of generators, the paralleling of generators, and the protection of generators. It is important to consult the NEC before installing or modifying a multiple generator system to ensure that the system complies with all applicable requirements. High voltage applications, which typically involve voltages above 600 volts, require special considerations to ensure safety and reliability. Firstly, insulation. Adequate insulation is crucial for preventing electrical breakdown and ensuring safety. High voltage equipment should be properly insulated with materials that are designed to withstand the high voltages involved. Secondly, clearance. Sufficient clearance should be maintained between high-voltage conductors and other objects to prevent arcing and flashover. The clearance requirements vary depending on the voltage level and the environment. Thirdly, grounding. Proper grounding is essential for electrical safety. The grounding system should be designed to provide a low impedance path for fault currents, allowing protective devices to quickly trip and energize the faulted circuit. Fourthly, shielding. Shielding can be used to reduce electromagnetic interference and protect sensitive equipment from high-voltage fields. Shielding is typically achieved by enclosing high-voltage equipment in a grounded metal enclosure. Fifthly, surge protection. Surge protection devices should be installed to protect high-voltage equipment from voltage surges caused by lightning strikes or switching operations. Sixthly, personal protective equipment. Workers who are working on or near high-voltage equipment should wear appropriate personal protective equipment, such as insulated gloves, sleeves, and hard hats. Seventhly, training. Workers who are working on or near high-voltage equipment should be properly trained in the hazards of high voltage and the safe work practices to be followed. Eighthly, NEC requirements. The NEC contains a number of requirements for high-voltage installations. These requirements cover topics such as insulation, clearance, grounding, shielding, and surge protection. It is important to consult the NEC before installing or modifying a high-voltage installation to ensure that the installation complies with all applicable requirements. Ninthly, arc flash hazard. Arc flash is a dangerous phenomenon that can occur when high-voltage equipment is energized. An arc flash can produce intense heat, pressure, and light which can cause serious burns and other injuries. Arc flash hazard assessment should be performed to determine the potential arc flash hazard at a particular location. The results of the arc flash hazard assessment should be used to select appropriate personal protective equipment and to develop safe work practices. Lastly, lockout/tagout procedures. Lockout/tagout procedures should be followed when working on or near high-voltage equipment to prevent accidental energization. Lockout/tagout procedures involve disconnecting the power supply to the equipment and placing a lock and tag on the disconnect switch to prevent it from being accidentally turned on. By following these guidelines, you can help to ensure the safety and reliability of high-voltage installations. The NEC plays a crucial role in ensuring electrical safety and proper installation practices. The NEC, or National Electrical Code, is a widely adopted standard for the safe installation of electrical wiring and equipment in the United States. It is developed and published by the National Fire Protection Association, or NFPA. The NEC is updated every 3 years to reflect changes in technology and best practices. The NEC covers a wide range of topics, including wiring methods, overcurrent protection, grounding, and equipment installation. It is used by electrical inspectors, contractors, and engineers to ensure that electrical installations are safe and compliant. The NEC is not a law, but it is often adopted by state and local governments as part of their building codes. This means that electrical installations must comply with the NEC in order to be approved by the local authorities. The NEC is organized into chapters, articles, and sections. The chapters cover broad topics such as general requirements, wiring and protection, and equipment for general use. The articles cover specific topics within each chapter, such as grounding and bonding, overcurrent protection, and wiring methods. The sections provide detailed requirements for specific aspects of each topic. The NEC is a complex document, but it is essential for anyone involved in electrical work. Electrical inspectors use the NEC to verify that electrical installations are safe and compliant. Electrical contractors use the NEC to ensure that their work meets the required standards. Electrical engineers use the NEC to design safe and reliable electrical systems. The NEC is a valuable resource for anyone who wants to learn more about electrical safety and proper installation practices. The NFPA offers a variety of training programs and resources on the NEC. These resources can help you to understand the NEC and apply it to your work. The NEC is constantly evolving to reflect changes in technology and best practices. It is important to stay up to date on the latest changes to the NEC to ensure that your electrical installations are safe and compliant. The NFPA offers a variety of resources to help you stay up to date on the NEC, including the NEC Handbook, the NEC Analysis of Changes, and the NEC Online. The NEC is a critical component of electrical safety in the United States. By following the requirements of the NEC, you can help to ensure that electrical installations are safe and reliable. The NEC is not intended to be a design manual. It is intended to provide minimum safety requirements for electrical installations. Electrical engineers and designers should use their professional judgment and experience to design electrical systems that meet the specific needs of the application. The NEC is not a substitute for proper training and experience. Electrical work should only be performed by qualified individuals who have been properly trained and have the necessary experience. The NEC is not intended to cover all possible electrical hazards. It is important to be aware of the potential electrical hazards in your workplace and to take appropriate precautions to protect yourself from these hazards. The NEC is a living document that is constantly evolving to reflect changes in technology and best practices. It is important to stay up to date on the latest changes to the NEC to ensure that your electrical installations are safe and compliant. The NEC is a valuable resource for anyone involved in electrical work. By following the requirements of the NEC, you can help to ensure that electrical installations are safe and reliable.